Bismillahirrahmanirrahim. Hello, dear students. I hope you are having a nice day. I welcome you all in class of Elementary Number Theory by David M. Burton. In today's lecture, we will discuss relatively prime integers and some theorems related to greatest common divisor of integers. These theorems actually represent the properties of greatest common divisor. So let us start from the definition. Uh, Two integers a and b, note both of which are 0, are said to be relatively prime if their GCD is 1. For example, 3 and 4 both are relatively prime because their GCD, greatest common divisor, is equal to 1. But if you find GCD of 2 and 8, this is equal to 2, that is the greatest common divisor of 2 and 8 is equal to 2. This shows that 2 and 8 are not relatively prime. So the integers whose GCD is 1 are called relatively prime. Is it possible that that one of them or both of them are negative? Yes. For example, uh, if one of the integer is -5 and the other is 13, now you can see here the greatest common divisor of both of them is 1. So 1 is the GCD of these two integers. But it is always remembered that we always take GCD as a positive integer. Next, the following theorem characterizes the relatively prime integers in terms of linear combination. This is the theorem 2.4 given in the book of David M. Burton. This theorem can be stated as let a and b be the integers, not both 0. Then a and b are relatively prime if and only if there exist integers x and y such that 1 is equal to ax plus by. This is not a new result. In the last lecture, we discussed that the GCD of two integers a and b can be expressed as a linear combination of a and b. So if here because integer a and b are the relatively prime, so by definition their GCD is equal to 1. So we can express 1 as a linear combination of this. So this is the necessary and sufficient condition that we have to prove here. Firstly, we suppose that if a and b are relatively prime, then GCD is equal to 1. We will show that 1 can be written as the linear combination of a and b. Theorem 2.3 guarantees the existence of the integer x and y satisfying 1 is equal to ax plus by. What was the theorem 2.3? Theorem 2.3 was this was theorem 2.3. Given integer a and b, note both of 0, then there exist integer x and y such that you can express GCD as the linear combination of ax plus by. So the first condition is satisfied by theorem 2.3. Now for converse, we suppose that 1 is equal to ax plus by. Now we show that their GCD of AB is equal to 1. As 1 is equal to ax plus by for some integer or some choice of x and y such that D is the GCD of AB. By definition, as D is the GCD of AB, so D must divides A and B both. Theorem 2.2 yields that D divides ax plus by. What was the theorem 2.2? Theorem 2.2 says that if one of the integer a divide b and a divides c, then a must divide the linear combination of b and c, that is bx plus cy. So here as d divides a and d divides b also, it means d must divide the linear combination of a and b. What is the linear combination? This form ax plus by is called linear combination of a and b. So if d divides a and d divides b, then d must divides the linear combination ax plus by. But ax plus by is now equal to 1. This is equal to 1. So this shows that by plugging ax plus by is equal to 1, we have d divides 1. As d is a positive integer, this last divisibility condition forces d is equal to 1. Part B of theorem 2.2 plays a role here. What was the part B of theorem 2.2? This part says that if a number a divides 1, then it is possible that there are the only two possibilities, that a is equal to plus minus 1. In other words, we can say that there is only two divisor of 1. One is plus 1 and other is minus 1. So when you say d divides 1, it means there are the two possibility for d. D is either equal to 1 or it is either equal to minus 1. But by definition, d is always a positive integer, so that's why d is must equal to 1 here. That is required to prove. Next we prove some corollaries related to this theorem, and this is very important corollary regarding your final exam. This corollary says if the GCD of two integer a and b is d, if we divide these two integer a and b with d, then their GCD of this fraction is always equal to 1. Firstly, we prove this corollary by a particular example. Suppose GCD of 2 and 6. What is the GCD of 2 and 6? Which greatest number divide both of them? This is equal to 2. Now if we divide both of the integer by this GCD, we have a fraction 1 and 3. Now if we find the GCD of 1 and 3, this is equal to 1. So if we divide these integer a and b by the greatest common divisor d, then the GCD of this fraction a over d and b over d is always equal to 1. In other words, we can say that this fraction is always a relatively prime integers. Further, you can notice that this is not a fraction. It seems a fraction, but it is always an integer. You can take any two integers. For example, if you take 5 and other is suppose this is equal to 15. Suppose, what is the GCD of these numbers? The GCD of these are 5. Now if you divide 5 by this GCD, again this is the fraction, but it is equal to 1, that is an integer. Similarly, if you divide 15 by 5, this is a fraction, but it is equal to an integer. So before starting with the proof proper, we should observe that although a over d, b over d have the appearance of fraction, in fact they are the integers, because d is a divisor both of a and of b. Now knowing that GCD of ab is equal to d, it is given. So it is possible to find integer x and y such that we can write d as the linear combination of a and b. Upon dividing on both sides by the d, we obtain the expression. When you divide this expression by d on both sides, we have d over d, which is equal to 1, a over d into x, b over d into y. Because a over d and b over d are integers, so by using above theorem for star, we have a over d and b over d are relatively prime. What is the above theorem? In this theorem, we have proved that if a and b are relatively prime, then their linear combination is equal to 1. Now, if you use this theorem in this example, in this corollary, and particularly in the star, you can notice that this is the linear combination of a over d and b over d, and these both are integers, and the linear combination of a over d and b over d is equal to 1. This shows that these two integers are relatively prime. Hence, we can write it as, if these are the relatively prime, then their GCD is equal to 1, which was required to prove. Corollary number 2, this is also very important corollary. This corollary says if a divides c and b divides c, that is a and b are the two divisor of c, such that the GCD of a and b is equal to 1, then ab, the product of a and b, must divide C. This is also very important. For example, 6 divide 12 and 6 divide 12 and 5 also divide 6 divide 120 and 5 also divide 120. Now the product 5 into 6, that is 30, must divide 120. Given that A divides C and B divides C, it means there exist integer R and S such that can be found such that C is equal to A into R and C is equal to BS. This is the definition of divisibility. When you say A divides C, it implies there exists an integer R such that you can write C is equal to A into R. This is the definition of divisibility. Similarly, when you say B divides C, you can find an other integer S such that C can be written as B into S. So in both cases, AR equal to BS is equal to C. Now using the relation as GCD of AB is equal to 1, so 1 can be written as the linear combination of A and B for some choices of integer x and y. Multiply the last equation by C. We have C is equal to C into 1, C is equal to ax plus by. Multiply C with the numbers inside the brackets. We have acx plus bcy. Substituting the values of A and B. What is the value of A and B? Substituting the value of C here. C is equal to BS and C is also equal to AR. So plugging the value of C is equal to BS here and plugging the second value of C which is equal to AR here. We have A into BS and A into BR. By taking common AB, we have SX plus RY. As X, Y, R, S, these four are integers, and we know that the sum and the product of two integers is always an integer. This shows that this whole sum is an integer. So we say, suppose this is equal to K. Then we have C is equal to AB into K. Again, by using the definition of divisibility, we can write it as AB divides C for some integer K. That is required to prove. Alternatively, we can prove this corollary. This is a very interesting and easiest way. Since it is given that A divides C and B divides C, so there is this positive integer K1 and K2 such that we can write C is equal to AK1. Say this is equation number 1, and we from this equation we can write C is equal to BK2. This is equation number 2. By creating equation number 1 and 2, because both of the equations are equal to C, so we can write it as BK2 is equal to AK1. This equation shows there are the two products here in this equation. One is BK2 and other is AK1. Both are equal. This implies that A must divides BK2. How this is possible? You can notice that. Are you agree that A divides AK1? Yes, A must divides AK1. But AK1 is equal to BK2. It means by replacing AK1 is equal to BK2, this implies A divides BK2. Now in the next lecture we will discuss the Acrid lemma that I am using here. Acrid lemma says that if a number A divides the product of two integers B and C, if the GCD of A with one of them is 1, suppose the GCD of A and B is equal to 1, then it must be that A divides the third number C. So as here A divides this product BK2 and it is given that the GCD of A and B is equal to 1. So by using Acrid lemma, Acrid lemma guarantees that A divides K2. Again, by using the definition of divisibility, we can write it as K2 as the multiple of A. That is K2 is equal to A times K3. Put this value of K2 in 2. What is 2? This is my equation number 2. So put here the value of K2. We have C is equal to B into AK3. That can be written as AB into K3. So C is equal to AB into K3. Again, by using the definition of divisibility, this definition says that, sorry, here will be AB divides C, which was required to prove. There are some important things that you can notice here. In corollary number 2 holds if corollary number 2 hold if A and B both are relatively prime. For example, as 6 divide 24 and 8 also divide 24. But their product 6 into 8, that is 48, does not divide 24. Why this happened? Because here GCD of A 6 and 8 is equal to 2, which is not equal to 1. That is 6 and 8 both are not relatively prime. That's why in this case the product of 6 and 8 will not divide the number 24. On the other hand, 3 divides 24 and 4 divides 24. This implies their product 3 into 4, that is 12, divides 24. This is now correct because the GCD of 3 and 4 is equal to 1 here. So in today's lecture, we will discuss the definition of relatively prime integers, some important theorems that are actually the properties of the greatest common divisor. So I hope now you have a clear understanding of today's discussion. In the next lecture, we will discuss a very important lemma that is known as Euclid lemma. So if you find my lectures helpful, kindly like, share and subscribe my channel. See you in the next lecture. Take care. Allah Hafiz.